All right, so this is the first homework problem you were assigned last night. This is what you were given. Now, what I told you yesterday in the notes is if this number, this subscript right next to the C, is less than 5, then this is going to be a gas. Okay? That was in your notes yesterday. Oxygen is always going to be atmospheric oxygen, O2, and that's always a gas. If you're grading their paper, you're actually supposed to be making corrections. You're supposed to be giving them information to help them be more effective the next time around. That's your job. Okay? All right, now, if we have a hydrocarbon fuel and oxygen, the products for this reaction are always going to be the same. They're always CO2, and that's always a gas, and H2O. And because of the heat that's generated in the combustion reaction, this is going to be a gas. Okay? In a combustion reaction only. If there's a lot of heat around, and combustion reactions produce light and heat. Okay? Combustion reactions always produce light and heat. That's one of the definitions of what a combustion reaction is. In its broadest form, a combustion reaction is any reaction with atmospheric oxygen that produces light and heat. Okay? So we're only going to we're going to limit ourselves to balancing and predicting products and such for very limited kinds of combustion reactions, those that involve hydrocarbon fuels and atmospheric oxygen. Okay? Now we're ready to make out an atom inventory. So we're going to put a C here and an H here and an O here. We're going to build that grid for the atom inventory, or chart, if you like to call it a chart, that's fine. Okay? And then we're going to count all of the elements we have. Okay, we have 4 carbons, we have 10 hydrogens, we have 2 oxygens. Over here it's 1, 2, 3. Okay? So now we've got to try to get all of the elements in our atom inventory to have the same number. And the only thing you're allowed to use to balance an equation are coefficients, leading terms in front of these symbols for these compounds. Okay? You're not allowed to change the numbers inside the formula, because once the formula is balanced, you can't change it around. If you do, you unbalance the formula, and unbalancing the formula isn't what actually takes place in the chemical reaction. Chemical equations represent what's actually going on in a chemical reaction. Okay? So I see that I have 4 carbons here. To get 4 carbons on this side, I need a coefficient 4 in front of the species that contains the carbon. But when I put the 4 in front, it changes everything in that formula. So we're going to be changing the number of carbons and the number of oxygens. So the number of carbons we now have is 4. But the oxygens we have now is 4 times 2, 8 oxygens here, plus the 1 here. So we currently have 9 oxygens. So we always balance oxygen last. So the next thing we want to do is to balance the hydrogen. That's the next to the last one you always do. So we've got 10 hydrogens on the left, 2 on the right. To get 10 hydrogens on the right, we need a coefficient of 5 in front of the water. That's because 5 times 2 is 10. So that's going to change this and change the number of oxygens. So we're going to put our 10 hydrogens here, and we're going to re-add all of the oxygens that we have. 4 times 2 is 8. 5 times 1, 5. So we currently have 13 oxygens. This is where you get to a place that a lot of students just kind of give up and go home. Well, don't do that, because fixing this is really easy. All you have to do is, when you have a situation like this, where you have an odd number of oxygens on one side and an even number on the other side, is this. You're going to, yes?
I'm sorry, Emma. How do you see 8 of you revising your 9
4 times 2 is 8.
And you added it to 1.
5 times 1. Well, before I put the 5 here, I added it to 1, yes.
So it's not going to be 9 plus 5, it'll be 8 plus 5? Okay.
Correct. Okay, all right, now, so what you're going to do now, when you have a situation like this, where you've got an odd number of oxygens on one side and an even number on the other side, is you're going to go through and multiply all the coefficients, except the one in front of oxygen, by 2. So since I have an implied 1 here, I'm simply going to put a number 2 here. I want to change this 4 to an 8. I want to change this 5 to a 10. Let me go back through and recount everything. And this changes everything except the oxygen on the left at the moment. Alright, so now I have 2 times 4, or 8 carbons. I have 2 times 10, or 20 hydrogens on this side. On the other side, I've got 8 times 1, or 8 carbons. The number of hydrogens I have is 10 times 2, that's 20. And so the oxygens, 8 times 2 is 16. 10 times 1 is 10. That's a total of 26 oxygens. So fixing the last coefficient should be fairly easy. What do I need to multiply 2 by to get 26? 13. And that'll give us 26. Alright? So that's how you handle those combustion reactions. Now, did I ask you in the homework yesterday to classify these? I did. So we're going to classify this then is combustion. Okay? Let's count the number of all the points we're going to give you. I'm going to give you a point for the coefficient 2, a point for having the right physical state here, gas, a point for 13, and a point for the gas here. I like to cross out the 4s and put an 8 here, but some people don't do that. That's fine. I want to give you a point for the correct coefficient when you get done, for the correct formula CO2, and the correct physical state. 10 here, I'm going to give you a point for the correct formula for water and the correct physical state. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points for the equation. Okay, alright. Then the atom inventory, you get 1, 2, 3 points for the element symbols. Now, up to now, most of the time I give you a point for the correct initial count, canceling that out, and then I give you a point for the next number. But you can get an answer to this problem in different ways. But what everybody has to have the correct answer is the first number and the last number. So I'm not going to count the points that come along with this middle number, or in this case 2 middle numbers. Only 4 cancellation 8. That makes sense? So 1, 2, 3, 4, 5, 6, 7, 8. Well, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 9 points for this. And you're going to end up with 9 points for this one as well. Okay? So that's a total of 21 points, right? And then the classification of combustion. Let's give that 5 points. So that problem total would be 36 points. All right. What now? All right, number 2. Number 2 is aluminum chloride, which I told you in the problem was aqueous, and that's plus calcium, and that's a solid. I really shouldn't have to tell you that it's a solid, because you can look that up on the periodic table and see that it's a metal, and except for mercury, all the metals we deal with in here, we said are going to be solids if they're by themselves. Okay, so if I have an element by itself, and I have a compound with an element that's like the element by itself, that is to say, in this case, a metal and a metal, then we're going to assume this can be a single replacement reaction, but only if this metal that's by itself is more active than the metal in the compound. So for that, you're going to need your test references. Christopher, did you have a question?
What does mercury do? You said it's not everything is good.
Yeah, mercury metal, when it's in its pure form, is a liquid.
So it melts if you put it in.
Well, it doesn't melt. It's a liquid. It's actually a liquid. If you put mercury metal in your hand, it's almost like a drop of water in there. Only it's bright.
Call it mercury metal. How is it a metal?
Because it is. It's still a metal. It's just liquid. You could say it melts, but at room temperature and pressure, it's already liquid, so it doesn't melt. If it melts, it starts out solid and becomes warmer in your hand and melts. And there are metals that do that. They're alloys, but they can't do that.
What if you freeze it? Like it's going to become...
Ed, it takes a really cold temperature to freeze mercury. I forget how cold it has to be. It's really, really cold. The reason they originally put mercury in thermometers is because you had to get it really, really cold to get it to freeze. That's one thing. And the other thing is that its expansion and contraction with temperature is very consistent. So originally, mercury was probably called quicksilver. Okay? So if you ever see that term quicksilver, there's a cartoon character, a comic book character called Quicksilver or something, isn't there? All right. So if you look at the activity series, here's aluminum and here's calcium. So calcium is more active because on the activity series it's higher. Calcium is more active than aluminum, so calcium will displace the aluminum. Okay? Therefore, the calcium is going to join up with the chlorine, and the aluminum is going to be by itself. Now that's a metal, and so that's going to be a solid. Okay? We need to figure out the physical state of this and balance that. All right? Calcium has a 2+ charge. Now you could look that up on the periodic table with oxidation numbers, but it actually is also right here. Okay? So if that's 2+ and chlorine is 1 negative, you know that chlorine is 1 negative. Well, you can look at it on the periodic table with oxidation numbers, but it also happens to be down here. Okay? If I have a calcium that has a 2+ charge and a chlorine with a 1 negative charge, and I need to have a formula that's neutral, cancel out all the charges, how many chlorines do I need? 2, and so we're going to have to have a subscript 2 here. Okay? Now we need to know if this is going to be aqueous or solid. Now, the reason I need to know that is because I'm in an aqueous environment. This aqueous over here means there's water around. So if this stuff dissolves in water, we're going to call it aqueous as well. If it doesn't dissolve in water, we're going to call it solid. So if we go to the solubility rules then, which is right above your activity series, then the second column or row here says that all chlorides, bromides, iodides, except those bonded with silver, lead, and mercury, and that's not bonded, it's about bonded to calcium, not bonded to those, are going to be soluble. So chlorides are soluble. In this case, this chloride is soluble. Since there's water around, it is aqueous, and that's the correct physical state. Now we're ready to balance the equation. So we're going to list all of our elements: aluminum, chlorine, calcium. We're going to make our grid for the atom inventory. Count up the atoms that we have. Got 1 aluminum, got 3 chlorines, and 1 calcium. Over on the other side, I've got 1 aluminum, I've got 2 chlorines, and 1 calcium. Okay, now, in order to get all the elements the same, I'm going to start with the chlorine. That's the only one that's not balanced right now. And the only way to get the same number of chlorines on both sides is to put a 3 in front of this species and a 2 in front of this one. Okay, that will give me 6 chlorines on both sides. So I'm going to put a 3 here and a 2 here. And that's going to change the number of aluminums and chlorines on this side and the number of calciums and chlorines on this side. So over here, I now have 2 aluminums and I have 6 chlorines. Over on this side, I have 3 calciums and 6 chlorines. So the chlorines are balanced. We just got to get the metals balanced now, or the metals that are by themselves balanced. I've got 2 aluminums on the left. I've got 1 on the right. My coefficient 2 will fix that. So now that's 2 aluminums, and if I've got 3 calciums on the right and only 1 on the left, a coefficient of 3 will fix that over here. And so this equation is now balanced. We're going to classify this as, alright, since I have an element by itself, that's replacing an element it's like in a compound, that's single replacement. Okay? So this is called single replacement, or you can call it single displacement. Either one is acceptable. Let's figure out our point scheme here. 1 point there, 1 point there, 1 for this, 1 for the calcium and chlorine being together in the subscript 2, and for the physical state. Coefficient 2, aluminum and solid. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points for the equation. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 points for the atom inventory, and then 5 points for the classification. So this actually comes out to be the same number of points, a total of 36 points here. Okay. Third problem, aluminum chloride and chromium. Okay, so the first thing we want to do is to see if chromium is more active than aluminum. Okay? Well, here's chromium. Let me find. There's chromium, and there's aluminum. So chromium is the metal that's by itself, and it's not more active than aluminum. Therefore, there's no reaction. And the only thing you have to write is NR. Now, you could classify this as single replacement, but since a reaction doesn't really happen, you don't really need a classification here. Okay? I'm only going to give you 5 points for saying there's no reaction. Okay? 5 points. Now, let's see. The next problem then is potassium fluoride, which I indicated was aqueous to start, and calcium chloride, which I indicated was also aqueous. Okay? So this is a 2-part compound here. It's ionic, metal and nonmetal. There's a 2-part compound. It's ionic, metal and nonmetal. We have everything we need to make a double replacement reaction if there's a driving force to make it go. Well, if what we need to do is find out how we're going to put it together over here to see if there is a driving force. Okay? So the front part of this compound goes with the back part of this one. All right? So we get K and Cl. Subscripts only travel automatically if they're part of a polyatomic ion. Chlorine is not a polyatomic ion, so this subscript doesn't travel automatically. Okay? And then we're going to put the calcium with the fluorine. Now I could balance the formulas now, but I'd like to find out the physical states first, because if I don't have a driving force, I don't have to do anything else really, except write no reaction. So I need to know if calcium chloride is aqueous or solid. We do have a water environment. These AQs on these 2 chemicals, our 2 reactants over here, indicate there is water. That's what aqueous means, dissolved in water. So I need to know if calcium chloride is soluble or insoluble. If it's soluble, it's going to be aqueous. If it's insoluble, it's going to be solid. So if I look on the solubility rules, I'll see that group 1 salts. Well, potassium is in group 1. It's in the first column of the periodic table. That's group 1 here. Okay? So, but that's going to be a group 1 salt. It says group 1 salts are soluble. That means when there's water around, it's going to be aqueous. It also turns out there are chlorides listed. Chlorides are mostly soluble. There's a few exceptions, but Potassium is not one of the exceptions, so for both reasons this is aqueous. Now let's look for calcium fluoride. Calcium is not listed here, at least in the beginning of these things, but fluorides are. And it says all fluorides are soluble except group 2, lead 2, and iron 3. Well, calcium is in which group? Group 2. It's in the second column here. Okay? So, since group 2s are exceptions, while most fluorides are soluble, group 2 combined with fluorides are not, so this is going to be solid. Alright, so now we're ready to balance the formulas. If you look up the charge number on the potassium, that's a 1 plus, and the chloride is a 1 negative. You find that on the periodic table of oxidation numbers that I gave you. You could also infer it from its position on the periodic table. Everything in column 1 is plus 1, and in a binary compound, everything in column 7A is negative 1. Calcium is in column 2, we said, and everything in column 2 is going to have a 2 plus charge. You could look it up on a periodic table that has oxidation numbers. Fluorides are in column 7A, and in a binary compound, everything in 7A is going to have a 1 negative charge. So to balance the calcium and the fluorine, I need 2 fluorides. So I'm going to put a subscript 2 here. Now that I've got the formulas balanced and I've identified that there is a driving force for this reaction to occur, I'm ready to balance the equation. So I'll list all the atoms we have, make our grid to keep up with the atom inventory, and count all the elements. 1 potassium, 1 fluorine, 1 calcium, 2 chlorides. On this side I've got 1 potassium, 1 chlorine, 1 calcium, and 2 fluorides. So I want to try to get everything equaled out, the same number of elements on both sides. I've got 2 fluorines on the right, 1 on the left. I can only use coefficients to balance this out. I can't do anything with the formulas. I've got to leave the formulas alone. So that 2 there will give me, we're going to change the number of potassiums and fluorines, and we're going to have 2 of each. That gets the fluorines balanced. Let's see, I'm going to go to, I could go back to potassium now. It doesn't really matter, but let's do that since I've already unbalanced it. Got 2 potassiums on the left, only 1 on the right. We can put a coefficient 2 here, and that'll change the number of potassiums and the number of chlorines. And we'll have 2 of each. Okay, 1 in the formula times 2 is 2. Oh, thank you. Chlorine 2. Alright. Okay, so now it is balanced, right? You're right, because I messed that one up. I put it in the wrong place. That's calcium has 1 of those. Okay, and that fixes it.
It's like, is there any deeper chemistry where, like, you would, I forgot what you said. Never mind. Oh, where you could put some inside the coefficient? I mean, inside the coefficient, like, like, is it?
No. Not that I'm aware of it. There's other kinds of equations where you can do something like that, but not in this kind of equation. You can't do that.
No, I'm saying, like, deeper since you're not this kind of.
Right. But what I'm saying is, if you're doing this kind of equation, no, you can't put numbers inside the formulas to change it. Okay? All right. That was number 4. Number 5. Oh, I guess so. I guess we need to give you points for it, don't we? Well, 1 point here. 1, 2, 3, 4 points there. 1, 2, 3, 4 points there. 1, 2, 3, 4, 5, 6, 7, 8. Is that right? No, 9. 9 points for the equation. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 points for this, for the atom inventory. So that's a total of 29 points. Okay. Now we're ready to go to the next one? Okay. What now?
The classification.
Oh, I didn't. Golly, I got. What's the classification? I'm having trouble here. Double replacement. Good. All right then. Next equation. Well, that's going to be 29 plus 5. That's 34, isn't it? I know, I'm getting ahead of myself. You're right. So that's 5 points for this. All right. Number 5. So we get H2SO3. And we got strontium hydroxide, SrOH2, and that's also aqueous. Okay. So we're ready to figure out now whether this is going to go forward or not. Now this is a double replacement reaction. I've got two two-part compounds. This H is the front part, the SO3 is the back part, SR is the front part, OH is the back part. We need to figure out if we're going to have a driving force. For a double replacement reaction, you have to figure out what the products are going to be first. So the H part joins up with the OH part. This subscript does not travel because it's not part of a polyatomic ion. This 3 will because it's part of the SO3, the sulfite ion. But this 2 is not. Okay? This 2 is not part of the polyatomic ion. There is a polyatomic ion, but the polyatomic ion is inside the parentheses. So the 2 is not part of it. Okay, so this H and this OH are going to join together over there. Okay, and you should know by now, we've done this enough now that you should know that this is a liquid, this is water. So, when we have a combustion reaction, the water product is a gas. When we have an acid-base reaction, the water product is a liquid. Okay, Deja, you got that? Because that's what you were asking about a while ago. Okay. Then the front part of this goes with the back part of this. Okay, and we haven't balanced that, nor have we figured out the physical states yet. However, I already know there's a driving force because we formed water. Okay? Formation of water is one of the two driving forces you have to know about in this class. Either the formation of a solid in an aqueous environment, or the formation of water in an aqueous environment. Either one of those will give you a driving force, and this double replacement reaction will occur. So I'm going to go ahead and balance. Well, do you want to balance the formula, or you want to figure out what its physical state is going to be? Okay, I'm not sure that sulfites are even listed, are they? No, I don't even have those on this solubility rules. So, well, wait a minute, hold on, let me see. Yeah, but that wouldn't really answer your question, so you wouldn't know. So we won't give you any points for correctly identifying that one. I'm pretty sure this one would be considered a solid, but we won't worry about it too much, okay? I won't give you points for that or not give you points. You know it's going to happen because you got this water. That make sense? You with me? All right. Now we have to balance the formula here. Strontium's in column 2 of the periodic table. All those elements have a 2+ charge. Sulfites have a 2 negative charge. So that's already balanced. Does that make sense to everybody? Okay. So now we're ready to balance the overall equation. Going to list our elements, H, S, O, S, R. Make our grid. Count up the elements we have. I've got 2 hydrogens here and 2 here. So I've got a total of 4 hydrogens. I've got 1 sulfur. I've got 3 oxygens here and 2 here. And I've got 1 strontium on the right-hand side. On the left-hand side. On the right-hand side, I have 2 hydrogens, 1 sulfur, 3 plus 1 is 4 oxygens. Everybody see where I got the 4 from? Okay. And I've got 1 strontium. You always save oxygen for last. That doesn't mean you have to write it last, it just means you balance it last. And you save hydrogen for next to last. So those are the only ones that are unbalanced right now. So I need to start with hydrogen. Okay? Since I have 4 hydrogens on the left and only 2 on the right, I need a coefficient of 2 in front of water. And that's going to change the number of hydrogens and the number of oxygens. So now I have 2 hydrogens in the formula times 2, so I have 4 hydrogens. I have 1 oxygen in the formula times the 2 plus the 3 over here. That's 5, and that's all it took to balance that equation. Okay? All right. Classification. This is the one kind of equation for which you must have 2 different classifications. Okay? It is double replacement. Oh. So that's the first one. And the second one can either be called acid-base or it can be called neutralization. Either one is acceptable. Okay? Alright. You're going to get a point for putting the 2 here, a point for the hydrogen and hydroxide making water, and a point for the physical state, a point for strontium and sulfates. We're not going to give you a point for listing it as a solid. You could have said it was aqueous. That's perfectly okay. So that's 1, 2, 3, 4, 5, 6 points for the equation. Then the atom inventory is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 points for this. And then you're going to get 5 points for each of these classifications. All right, for this one and either this or this. Okay? So 6 plus 16 is 22, plus 10 is 32 points. All right, we're almost done. Last equation. We had magnesium nitrate, aqueous, calcium chloride, aqueous, and we want to figure out whether or not, first of all, we're going to have an equation that's going to occur. So for double replacement reactions like this, we've got 2 2-part compounds. This has 2 parts, this has 2 parts. So the likelihood is if there's any reaction at all, it's going to be a double replacement. So the magnesium on the front here goes with this over here, with the back part of that. The calcium is going to go with the back part of this. So I could balance the formulas, but let's figure out the physical states first, because that's what we need to know there's an equation or not, that it will occur or not. So chlorides are always soluble unless they're bonded with silver, lead, or mercury. Well, that's magnesium. It's not an exception, so this is going to be aqueous. Okay? Nitrates are always soluble, and there are no exceptions. So we have not formed solid, water, or any kind of gas, so all you got to do is write NR. Okay? Yes, sir. Sure.
Just if they put single instead of double, like how they point that off the classification.
5 points.
The whole thing?
Yeah, because that's double replacement is the name of the classification. Okay. Anything else? Really?
Yep.
Well, Patrick says it's 140. You said 148?
Yes.
Hey, Harry can make them one.
You got it.
Hey, do you mind, Harry? Yep.
You got it on. It's a 5.2.
Okay, so the total for the whole homework,
What total was number 4? You got it. Not an N on it. Yeah, I mean, sorry, total was number 4.
Number 4, total of 34 pounds.
Yeah. I feel like on here.